Good afternoon. Welcome today. It's great to have all of our students here with our esteemed panel. We're going to be talking about data centers and the massive explosion of data centers for AI. I'm Dr. Michelle Marcolongo, the Dean, Drosdick Endowed Dean of Engineering here at Villanova. So it's great to see all your faces here. We're excited to talk about all of these amazing things coming. This particular session is part of a yearly series that we have called the Ward Lecture, which was started by Patrick Cunningham and Susan Ward. It's an Endowed Lecture Series in engineering. Susan Ward is a 1980s graduate of chemical engineering from Villanova and a university trustee. She and her husband, Patrick, established this lecture in 2009 as a means to bring big ideas to engineering, to our campus, and to the benefit of our engineering students. I think there's no bigger idea that we'll be able to cover than this topic today. The demand for data centers to power AI is tremendous. In Pennsylvania alone, there's been over $75 billion investment in updating hydrothermal power plants, refabbing a nuclear reactor, updating power grids, and building physical data centers by Google, Microsoft, Amazon, Blackstone, CoreWeave, Energy Capital Partners, and PA Data Centers, to name a few. This is an exploding area of engineering to physically outfit the data centers that will drive the AI revolution that we're finding ourselves in today. And these facilities, they're not just so massively large, they're also hungry. They're hungry for power, for water to cool their systems, and other coolants to cool their systems, and they need space. I think we're in an interesting inflection point because the global data center capacity has roughly doubled in the past 5 years, and AI workloads are accelerating that growth even faster. Some projections say that data centers could account for over 10% of total US electricity demand in just 5 years. To put that in perspective, the project demand is not far behind what it takes to power all of the homes in America. The US Energy Information Administration thinks that that amount is just going to continue. So what does it mean? It means that for our society facing some new critical questions, and questions that you, as our future engineers, are going to be able to solve. First, there's an infrastructure challenge. It's not just talking about data centers, we're talking about electrical grids handling these, whether we have enough renewable energy capacity. We can't really innovate fast enough on cooling technologies right now, because cooling computers alone can account for about 40% of the data center's energy use. So how do we create this infrastructure and the support network of human beings to operate these data centers and design and implement them? Second, there's sustainability considerations. Will we choose to make sustainable decisions in the fast construction and cooling of data centers? Here at Villanova, one of our goals, I hope you'll be starting to see this soon in your classes if you haven't already, we would like to make every Villanova engineer a sustainable engineer. It doesn't mean you have to do a minor or a master's in sustainable engineering. It means that in your design classes, we've already started to integrate sustainable thinking and sustainable design so that whatever your designs will be going in the future, sustainability is on the front of your mind. We build this into our systems early in the process so we don't have to go in later and fix them to correct environmental challenges later. And finally, there's the innovative opportunity. The challenge driving some of the most exciting engineering work happening now: liquid cooling systems, next-gen chip architectures to do more with less power, edge computing that distributes processing closer to where it's needed, renewable energy integration. These are not abstract problems, things that you're just going to be reading about. These are problems that are being solved now. And today's panelists are expert in these different areas of data center analysis and design. They're going to talk about what's technically possible, what's economically feasible, and what's truly sustainable. I hope you can all think critically about what you hear and how you may think about data center design and construction and utilization in your careers going forward. One of the most prominent engineers working at the forefront of the data center revolution is our own Dr. Al Ortega, the James Birle Professor of Engineering Technology in the Department of Mechanical Engineering here at Villanova. Dr. Ortega is a world-renowned expert in thermodynamics and thermal management system. He also co-leads our NSF-supported research center, where researchers from academia and industry collaborate to optimize performance and reduce the footprint of data centers. Through the Center for Energy Smart Electronic Systems, Dr. Ortega and colleagues are working hard to find sustainable solutions for data center operations, including advanced liquid cooling systems for server racks and waste heat recovery systems. Dr. Ortega will be moderating the panel discussion today, and so it's my great pleasure to introduce him to the stage. Thank you.
Thanks. Great. I don't want to be double mic'd. We're good? Good afternoon, everybody. So you honor us by attending the panel today. Our distinguished speakers come from afar. They're not next door. They come from Washington State, from Atlanta, Georgia, and New York State to be with us today. So as Michelle mentioned, in 2010, we were fortunate enough to get funding from the National Science Foundation to establish the Center for Energy Smart Electronic Systems. We had the goal to investigate energy efficiency and thermal management, power management in electronic systems. And we quickly realized that what we're really talking about was data centers more than anything. That was 2010. And so we find ourselves about 10 years later, about 2020, suddenly at the forefront of research in what is now emerging as one of the critical infrastructure engineering challenges of the century. And so we find ourselves in contact with many industry experts, engineers, physicists, scientists. And among those people are the people that I invited to come to the panel today. And I would say that we're fortunate that they immediately said yes. And I am fortunate because I've known our three panelists for a long time. I can call them my friends as well as my colleagues. So I'd like to introduce them to you and ask them to come on the stage. So Dustin Demetrio is from IBM, where he's at. Dustin is a senior engineer in the Advanced Thermal Energy Efficiency Laboratory at IBM in Poughkeepsie. He is focusing on advancing cooling technologies, cross-brand thermal development, and state-of-the-art data center designs for IBM. He received a PhD in mechanical engineering from Syracuse. Currently, he's focused on analysis, application, and optimization of energy conversion systems, particularly in high-density data centers and high-performance buildings, and in the development of advanced cooling technologies. I will add that Dustin, despite being a young person, a young engineer, has been quite influential already in leading the industry through his leadership in establishing needs and standards for liquid cooling through especially through the ASHRAE organization, and especially through the Technical Committee 9.9, which is charged with establishing standards for the industry. Thank you very much, Dustin. Sean James. So Sean is a senior director of data center research at Microsoft Corporation, where he runs data center research and development program within the cloud operations and innovation area. This organization provides the foundational cloud infrastructure for over 1 billion customers 20 million businesses, and 200 plus Microsoft online services in 90 different markets. Sean drives new technology for Microsoft's next generation data centers, including evaluation, development, and testing. Sean joined Microsoft in 2006 to manage operations at one of its data centers. Later, he joined the construction team and oversaw the design and building of new Microsoft data centers. So I just wanted to say a couple of other things about Sean. I've known Sean since the beginning of our research center. In fact, one of the first research data centers, or one of the first data centers that I visited, was at the invitation of Sean, and I just have to tell you really quickly that story. Sean invited me to go to this data center, and he says, but I can't be there, I'll meet you there. He sent me directions for how to get to that data center. So I show up in Seattle, fully expecting to see the data center in Seattle or Redmond or somewhere around there. But instead, he led me on a wild goose chase over the Cascade Mountains into the center of Washington State. And I told myself, where in the heck am I? Well, somewhere here is a Microsoft data center, and indeed I found it. And what I found was it's actually by the Columbia River, which I passed on the way. I said, oh, I see why this data center is by the Columbia River in the middle of nowhere. And that was wonderful because the next morning we opened our hotel doors and there's Sean. And that was a really great start to understanding that whole industry. Thank you for coming today. One other thing, Sean has led lots of innovative projects for Microsoft, including putting a data center into the ocean, just as a demonstration of being able to cool in this innovative way. Another thing that I know Sean worked on was putting hydrogen fuel cells directly into an equipment rack to provide on-site, on-demand power using gas instead of the power grid to provide power to data centers. Thank you very much, Sean. Lastly, David Quirk. Dave? So Dave is a serial engineer, entrepreneur, and currently the president and CEO of DLB Associates. So DLB Associates is named after a legendary data center executive and engineer named Don Beatty. So Dave went to work for Don, learned the data center business, or maybe taught it to Don, I don't remember, but eventually took over the company, which is quite impressive. He's got more than 25 years experience working in this mission critical industry. As CEO and owner of DLB Associates, consulting engineers, he leads a team of 500 plus associate consulting engineers, focusing on empowering innovation and transformative change in the built environment. He's chaired the technical committee, the TC 9.9 committee, mission critical facilities, data centers, technology spaces, and electronic equipment for ASHRAE, and he's contributed to many other key industry standards and committees. I think you can tell by my introductions that we have three people who are truly thought leaders in the data center industry, and so we are unbelievably honored that you all are meeting us today. So I'm going to sit down, let's start a conversation. So data centers are not new, right? Can you hear me? Yes, okay. Data centers aren't new. Data centers have been around for a very, very long time. And even though suddenly they're in the national consciousness, that's only because of the recent AI boom, right? So can we talk a little bit about the history of data centers, and in particular, can you say a bit about how they have evolved over the last, say, 20 years, and to where they were about 5 years ago when suddenly things took off? Can we start the conversation that way? Sean, can you start the conversation?
Yeah, you know, it's really interesting because when I started in 2000, actually when I was getting out of the Navy in 1997, the base I was on was just installing this thing called a data center. And I'd never heard of this thing before. It was this very, very cold room, and I really didn't understand it. It wasn't until I got to Microsoft where I really had that, oh, okay, now I understand why this is a very special room. So here's the history of data centers from Microsoft. And I think a lot of tech companies can sort of mirror this. But somebody at Microsoft had an idea that, hey, we could be producing and giving and distributing online services. So many people maybe remember MSN. And you could go there and you could search for cars and you could see the news and all that kind of stuff. I mean, that started basically with somebody who was focused on the software, but had to put that on a computer, and that computer was underneath this person's desk, and it wasn't serving very many people, and so that was good enough, just right underneath that desk. Yeah, sure, got a little warm in this room because the server's putting out a lot of heat. Every once in a while, that person might accidentally bump the power cord, and then that would go off, and the website, wouldn't be available. But only a few people were impacted. But as that website started getting more and more popular, now all of a sudden issues started popping up where one server wasn't enough. Now you needed 2, and then you needed 20, and 200, and 2,000, and 2 million. So you can imagine it's not feasible to scale the underneath the desk computer up to thousands of computers. So then this cluster of servers ended up in a network room at the end of the hall, and you can see those around here. You can hear some buzzing going on, and if you open up this room, you'll see a bunch of computers. They're put on racks so you can direct that airflow. This is the first time there was so much heat involved where you needed to actually direct the airflow so it wouldn't get sucked back in. There was also this concept of a battery, or if somebody bumped the power cord or if the power went out outside, then that server would keep running. But eventually, these server clusters outgrew these computer rooms. And then it was time to actually dedicate parts of whole buildings to this. And at the time, a lot of office buildings were just retrofitted into data centers. As a matter of fact, if you go into modern data centers today, you'll see a lot of artifacts from office data centers, like, what's that doing in here? Look, it's just because we've been slowly iterating over time. When I started at Microsoft in 2000, I was at a data center that drew 6 megawatts of power. And at that time, that was huge. 6 million watts for one building. But what was interesting is the way the building was laid out, it really reminded me of the submarine. So before I was at Microsoft, I was in the US Navy in a submarine, and here's the interesting thing about mission critical environments like submarines and like data centers, is there's a few things. Number one, there's always a backup. If anything goes down, something else will come in and keep things running. You can do maintenance concurrently without having to take the system down, right? Obviously that's important. There's all these features. That's the same sort of engineering methodology that's inside of a data center as well. And so as this mission critical system sort of grew over time, the amount of power that was needed continued to escalate, the amount of cooling that was needed, because every watt of electrical energy that goes into a data center comes out as, it needs to be cooled, right? It comes out as heat, it needs to be cooled. Until where we're at today. And I think we're going to spend the rest of this panel talking about sort of where we're at today. But it all starts with this need to sort of have a computer that you could keep cool and keep the power on at all times.
What was the first data center you ever went to, Dave? And
it would have been the late 90s. I worked a lot on the telecom, so like many of us from the data center industry, we started our roots off in the telecom space. So all of the big telecom companies that were building out their infrastructure around the country would have different points of presence, or POPs as they would call them. And that was my first introduction to, quote unquote, today's data centers. And it would be in the 90s. But if you fast forward a little bit, we had this little thing called a Blade server that came out from a little no-name company called IBM. And that was one of a few important step functions that brought us where we are here today. So that was the catalyst, literally, to get ASHRAE TC99 started. So we started an industry standards group and consortium to bring all of these ideas together from the IT OEMs and kind of standardize on what was acceptable to how to cool this new, hotter thing. And to Sean's point, we had to manage the airflow now. We had to purposely direct the airflow and create what we call today hot aisle and cold aisle. And fast forward a little bit more, we had something called virtualization. And it was a one-time step function where we could consolidate a lot of software on a single server. And that made it even hotter. So we had this change in the hardware, we had a change in the software. Those were two really important step functions that got us to a denser data center world that we're in today. And then along came AI, and it's the biggest step function so far.
During the evolution of the data center industry over the last 20 years, we've seen a lot of changes. One of the changes that I would like for you to comment on is the change in big companies owning and operating data centers for their own use, and the emergence of companies that are operating data center as services, right? What we now call colos. What have you seen, Dustin, in this world as a person in IBM, but just in general in observing the industry?
Sure. Yeah, so actually I'm going to go back more than 20 years. I'm going to go back to the late 1960s. So back in the late 60s, IBM had these big mainframes. No?
You might be adjusting your mic.
I think the data center just went down.
Yeah. AI's fault.
We're just going to give you this one.
All right. Is it?
Your shirt lapel.
The Ben plus one.
N+1, yeah, we never go down. I feel like this was foreshadowing because we talked about this a little bit earlier. Anyway, so back in the late 60s, IBM had these big mainframe computers. They took up the size of this room. If you've seen the movie Hidden Figures, in that movie they show these mainframe computers that were used to send the Apollo missions to the moon. And so the way the industry kind of progressed was, every company that wanted one of these things had their own space. We'll talk about liquid cooling later. At that time, it was all liquid cooled. And as it progressed, as companies needed data centers, they put them into their company, right? They own them, they operated them, they managed them. And, that paradigm has changed over time to, really still companies doing that, and there's lots of reasons we can go into. The need for security, maybe you don't want somebody else to manage and operate the data center. But, we have also seen, companies think about their core competency as a business. So you imagine you're a financial institution. Well, what's your core competency? It's finances, right? You probably don't want to be running and operating a data center, and so that's where this concept of co-location companies have come from, where you would rent space, power, cooling infrastructure from one of these colo companies, and let them manage and operate that. And then beyond that, as Sean was alluding to, right? Then we got to the world of software as a service, where you would want to use something like Microsoft 365, right? And what do? You go, you log in, you put in your thing, and you can pull up Microsoft Word and Microsoft PowerPoint and that whole public cloud model. And all of these have just been different paradigms as far as who owns and operates and manages the data center infrastructure, right? And it's really an abstraction, right? Having to have core competency, understanding all the hardware, to then, I think of this like the model of, renting versus, buying a house or staying in a hotel, right? You stay in a hotel, you don't really bring anything, you just bring your clothes. When you kind of rent a house, they're responsible for lots of things. That's kind of the colo model. And then if you're the enterprise data center and you want to buy the house and you want to be responsible for the maintenance, you want to do that, right? So it's kind of a similar model, but it really comes back to, how does a business look at this from the perspective of what's their core competency, what are the things that are important to them, and, which one of those models fits. I will say, I work with a lot of major corporations, and nobody is doing just one of those things, right? It's what we call hybrid, right? It's some combination of all of those things that makes sense for a business to do, right? And so
So how about a show of hands? How many of you live in a multifamily apartment or a dorm currently? Show of hands, come on, put them up high. It's all right, no judgment. Okay, that's a colo data center. That's it, it's as simple as that. So was it cheaper to rent a dorm or that multifamily apartment, or go out and buy your own house on a couple of acres? That's the economics of why the data center industry has shifted to the colo market. So a lot of companies used to build them themselves, and to Dustin's point, They would have their own data center, their own small site, but when you put them all together and you get that economies of scale, it's cheaper. And back to Dustin's point, it's not part of their core business to own and operate data centers. It takes a ton of people and resource to make that happen. So they just don't want to deal with it. They just cut a check to somebody else to manage most of it.
So I just want to tell one story about my own experience. Maybe it brings us to the, shall we say, the apex of the current era, air-cooled data centers. The first mega data center, the so-called hyperscale data center that I ever visited was in Luleå, Sweden. Now, if you look it up, Google it, you'll find that it's really far north in the world. And it was operated by Facebook. It was a gigantic, very large data center in Sweden operated by Facebook. And as an engineer, I have to say that I was really unbelievably impressed by the engineering of this fantastic facility that was engineered to deliver cooling air to all of the electronic machines in the data center. It was engineered to pass the cooling air through the the racks with the electronic servers, collect the hot air from behind the servers, send it up into a second-story plenum space and back to the system that cooled the air back down and send it back into the data center. So for me, what was so impressionable is A, I wish more people could see this feat of engineering because it was just unbelievable, the scale of it. The scale was incredibly huge. Secondly, what I think was particularly impressive was the fact that it had been, the entire building, the structure, had been engineered to perfection to deliver this cooling air to the entire system. But it didn't take, it wasn't overnight. Those concepts took 20 years probably to perfect. This idea of separating the cold air from the warm air, cold air, warm air isolation. So here we are to this level, and everything's going along fine, and then all of a sudden we get a big disruption, which is this big AI disruption, right? So let's shift our discussion about what happened. So we know everything has changed. It certainly has changed the data center industry. Can you explain to our audience what is fundamentally different, right? What is it that changed, and how did it disrupt the industry? Anybody, kick it off.
So the density, they're a lot hotter. So the average cloud data center today is about 10 kilowatts a rack. Anybody know what that's equivalent to? 10 kilowatts a rack? Okay, anybody have a fireplace at home? Or wherever you're at? Okay, that fireplace is about 10 kilowatts. But I'm not talking about sitting in front of it, 10 kilowatts. I want you to put your head in the chimney, that's 10 kilowatts. Right? Seal off the front of it, put your head in the chimney, now you're experiencing 10 kilowatts. That's the average power density in the average rack in the average cloud data center today. Now, for the liquid-cooled stuff we're talking about on the AI side, we start at about 40 to 50 kilowatts a rack, or 4 to 5 times that amount of heat. Now remember, your head's still in the chimney. It's kind of crispy at this point. And so now we're going to go up to racks that are already being deployed right now, 120, 300, 400, 500, 600 kilowatts a rack. 60 times. What's left of your head in the chimney? That's in a single rack. And Al and I were just on some panels where we were talking about beyond a megawatt or 1,000 kilowatts a rack. So what's changed? That density. We've gotten way, way denser in the rack, all driven by what? AI. So we've had this fundamental software change that's driven a change in the hardware. It's a lot hotter, and hence we need to change the way we cool it. Can't do it with the air anymore. That would be one heck of a hot stack going out. And so we had to find a different way. And now we're looking at different fluids, different liquids to take care of that heat.
So I know all of you have some way to explain to people what a megawatt is. You know, how big is a megawatt? Because these days now we're talking about the core facility in a data center is a 1 megawatt rack.
So what's a megawatt? How do you explain that to people?
Has anybody ever been at their house and plugged something in and turned something on and tripped a breaker? Okay, so you probably tripped maybe a 15 amp breaker. So think about the amount of power that's involved with that. The entire house is maybe, so that's one breaker, one room. The entire house is maybe using between 2 and 3 kilowatts, 2 and 3,000 watts. So we're talking about a building that's many million watts. And now we're building data centers that are even more than that, thousands of megawatts, so billions of watts of heat and power. So power in, heat out. I think one of the things that I just want to make sure everybody understands is why does AI need so much power? So conventional data centers, there isn't a lot of like hardcore compute needed. These things aren't like modeling, climate change or anything like that. They're basically just moving information around. And so, for example, if I was to take my phone, like I'm about to, because I need to send my niece a selfie, I always do that. And so the minute I take this picture, my phone's gonna upload this to some data center, and it's gonna go right to a server, and then that server's gonna immediately copy that picture across a bunch of hard drives that are on there. Because hey, what if that one hard drive crashes? Now I lost my picture, and that's not, I demand my picture be available at all times. Well, what if that whole computer goes down? Well, that picture has then been transferred across to other servers. That one server goes down, my picture is still on there. But what if the whole data center goes down? And now that picture has been transferred to other data centers as well. So it's not a lot of hardcore computing. It's just a lot of like keeping your information where it needs to be. Now think about, does anybody have a gaming computer in here? Yeah, okay, so your gaming computer probably has something called a GPU, a graphics processing unit. And at some point, we needed graphics that were so cool, we needed a dedicated chip to process just graphics, right? A GPU is good at doing certain calculations. Well, somebody figured out that you could apply that GPU to the type of calculations that are needed for machine learning and AI. And that was the game changer, because you can do things with GPUs that you can't do with regular CPUs, like pack an enormous amount of transistors on them. And that's what's creating this enormous demand of power and for heat. It's that GPU that you have to run. So hopefully that helps kind of clarify why AI is making things more hot now than it was back in the day when just your Insta pictures were floating around.
And I'll also add, right, to that. So back in the early 90s, we went through this transition where we had these, what we called bipolar transistors. And at that time, power was going up exponentially, and then the physicists invented this CMOS transistor. And what happened, we saw this complete drop in power, right? So in terms of performance per watt, we got huge gains in how much we could get out per watt, and the industry went to air cooling. So if you've has anybody heard of Moore's Law? People heard of that? Yeah. So Moore's Law was a very famous law, if you will, that Gordon Moore was the founder of Intel, who projected that every 2 years or so, you'd be able to double the performance of a processor chip, and you would do that at roughly the same power, and that was kind of what the industry had done. And so the other thing that's happened in this industry is that Moore's Law is sort of diminishing, right? Just to give you a perspective, right? So today we're building semiconductors at scales of transistors that are on the order of 2 nanometers, right? We're talking like atom scale transistors that we're building into these processing chips. And it's diminishing. And so the industry is trying to come up with more new ways, as Sean just mentioned, GPUs. The other thing that AI demands is getting things as close to each other as possible. So we have this new paradigm where not only do we have a silicon chip for logic, but we have this thing called high bandwidth memory. So getting memory as close to the compute as you can, right? Why? For performance. All of this is driving huge densities, as Dave mentioned. It's driving huge thermal challenges in terms of actually taking that technology and scaling it to get the performance you want. And so it's partly we're reaching kind of laws of physics too, almost. Like literally we're building things with the atom scale, right? And you know, if you've heard of quantum computing, right? That's kind of the next thing. How do we now take this to the quantum scale, right? And so it's partly laws of physics too that we're running into while still needing all of the performance and the benefits that we're getting from AI and all these technologies, right?
That's incredible. So I was asked to comment to a Delaware newspaper about a data center that they were planning there, and they told me it was going to be a gigawatt data center, or 2 gigawatt data center. And I ran some numbers, but in case you didn't catch it, right, we're talking about 1 megawatt racks inside of these data centers. By my calculations, that's about 500 to 1,000 homes, right? That's about 500 to 1,000 homes in one equipment rack. And so then that equipment rack is going to go into a gigawatt data center. So according to my calcs, you could power the city of Wilmington, Delaware with that power that's going into that data center. So I want to come back to Dave, something you mentioned earlier, which is my question. Why do they have to be so dense? Why do we have to concentrate so much computation and so much power and so much everything in one location? What's driving that?
The occupant of the data center. Does anybody know the occupant? And those that were in the room previously, you can't answer this. Anybody? Who's the occupant in a data center? Software. Software is the occupant. Software is what drives all this change. It's also what's driving the density right now. And so, just to steal what Dustin said, we're running up against the laws of physics. And one of those laws that's really problematic for us is this thing called the speed of light. It's too slow. It's too slow, and it's creating havoc in the data center space. And I'm not joking. And so we have to do these really complex computations. And in order to do those complex computations, we have to do a bunch of them all at the same time on a whole bunch of different chips. And then we have to compare notes with each other. And we have to do that in real time because we're trying to move on to the next computation. And we can't move on to the next one until we compare notes with one another. So the time, the distance to compare all of these is lag, latency as we call it in the speed of light world. And that latency, even though it may be a nanosecond, is too long. And so we have to pack all this stuff together closer and closer because otherwise we have to chew up additional processing power and cooling in order to deal with that lag if we spread stuff out. And so GPUs, they're great at this particular type of computation to do artificial intelligence transformers, this mathematical model that we got to run. But in order to do it at the scale that we have to do it, we have to cram all of it together as close as possible so that we don't waste additional energy doing those computations. And that's what's driving these gigawatt scale campuses. And to put that in perspective, that's like, roughly 1 million homes. You can do the math a bunch of different ways. Or 1/8 the scale of the entire city of Los Angeles in 1 gigawatt campus. And right now, we're building several gigawatt plus size campuses just here in the US. These things are massive. They are a city into themselves. It takes almost a city to build it because there's tens of thousands of people that we have to bring together to build one of these 1 gigawatt campuses.
That's pretty incredible. And so we're talking about such enormous increases in power that, of course, all of us have heard about power now. All of a sudden, people don't even care about power, are now worried about power. For example, is it going to raise my utility rates? Yeah. If they build a data center in my neighborhood, is it going to cause me to pay more out of pocket, right? Mm-hmm. But let's go more fundamentally to that. Where are we going to get all this power, right? If we're seeing such great increases in power utilization, where is it going to come from? First of all, where are we getting it now, and where will we get it in the future? Dustin, maybe you can kick us off on that.
Sure, yeah. So where is the power coming from today? It's coming from the same place you're getting the power to power this building, right? It's coming from the electricity grid, right? So If you've heard of Ashburn, Virginia, so it's, Data Center Alley is kind of the nickname, right? I don't know, Dave probably knows the numbers, but you walk there and all you see is data center after data center after data center, right? And they want more and more power, right? The utility companies there have basically said, we can't get you enough power, right? And even if you were able to get the power to generate the power, you can't distribute the power. We don't have transmission to distribute it, right? And so fundamentally, the challenge is that we're getting the power for all these data centers from the same grid and the same infrastructure today that we're also trying to power all of the other things that we need as a society, houses, college campuses, you name it, right? So I think that's the big challenge, and I think it's why you've started to see, I'm sure other panelists can talk more about this, but investments from some of these large data centers in things like on-site power generation. And Al mentioned, I think earlier about restarting nuclear power plants, right, to bring up the generation for this power. You're also seeing more, kind of what the industry has called like microgrids, right? So how do you actually take the data center off of the utility grid, or maybe treat the utility as a backup power source, but have the power that you need generated close to the data center so you're not disrupting the local communities, right? I think these are grand challenges. On top of that, I think, and we'll talk probably about sustainability, right, and what we need to do a little bit later, I think as we start to think about the power, we need to think about how do we do this responsibly, right? So it's not just about having power, it's about how do we have carbon-free energy or renewable energy sources, and how do we bring those into the grid so that when we're powering these, gigawatt campuses, we're doing that, environmentally responsibly also, right? So I think this is, grand challenge that the industry has.
And this is where we need this group and folks like you, is because we need to engineer a data center that is sustainable. And when I say sustainable, not just because it's a good thing to do, because we want to have, but we will not be able to grow if we don't have enough energy. We need a system that we can sustain growth, so it's not going to use up all of the water that's available. It's not going to use up all of the natural gas that's available. It's not going to create. So I mean, this is the grand challenge that we're talking about up here, because the old model of building data centers, it is not scalable. It is not sustainable. Where you just build a gigantic, billion-watt building and just plug it into the grid. I'm sorry, they can't build power plants fast enough. Okay, so as you said, so my data center industry, first of all, we're crazy. We're like, oh, we'll just build our own power plants. I mean, to be perfectly honest, that is not sustainable for more than one reason. Number one, all of the emissions that are associated with it. But number two, we're not power plant people. We're not energy people. So this might be a stopgap, but we need much better solutions. One of those solutions could be, can you integrate the data center into the grid better? And so what's going on right now is we're trying to figure out ways to integrate the data center into the grid, and now what you see is the compute system isn't just the server, it's not just the data center, but it's the server, the data center, and the grid. All these things have to work together really, really well. And this is where there's all types of awesome engineering challenges. Power challenges, cooling challenges, grid dynamics, all kinds of very, very interesting stuff. But we're sort of looking to fresh ideas at this on this problem.
Most of the grid right now is powered by coal-fired power plants, and it's about the most energy efficient, but it's the most environmentally inefficient. So it puts off lots of carbon into the atmosphere. So the stopgap that Sean's mentioning is to use natural gas. We happen to have a ton of it available now, and we have it because we came up with new technologies to draw it out of the ground efficiently. After that, we'll be shifting to nuclear, small modular reactors. And somewhere along the way in between, there'll be more renewable. But renewable still relies on the need for batteries, and lots of them. And now batteries have competition with what we need in the data centers and what we need in the automotive space. And so getting enough batteries manufactured to scale up renewables is a big challenge globally. and it uses a lot of energy just to make all the batteries and mine all the materials for them. So there's a combination of those things in flight right now. We're extending the life of coal-fired power plants. We're putting new natural gas ones online. We're adding more renewable into the mix to the extent we could get battery to back it. And we're working towards nuclear solutions downstream of that, which are still another 5 to 10 years out, but there's a tremendous amount of work going on that front now.
So I know there are some things that get a lot of press, unfairly maybe. Elon Musk's Colossus data center gets a lot of press, right, because it's so large. But it does point out maybe a solution of on-site power generation. They're putting gas-fired turbines in the backyard in that data center in order to provide on-site power generation. So is on-site power generation, I know, Sean, I know I've read your posts. I know you have opinions about on-site. Is that an intermediate thing, or is that a permanent solution maybe for data centers? Maybe somebody else builds your on-site power, but not your company. What's the future? Or are we depending on the entire infrastructure to grow up, meaning nuclear probably? What's the future? What do you all think is the future?
Yeah, we'll see. It's going to be very interesting. So when I talk to utilities, their mission is affordable power for everybody. So making sure everyone has power and making sure that power is affordable. And so that creates, in the nature of that industry, like a nature of an animal, the nature of you and I, the nature of that industry is to be very risk adverse. So then you got the crazy data center people showing up, waving their hands. Oh yeah, we need 3 or 4 more power plants, and this and that, the other. 3 or 4 more power plants. Well, that's like a 15-year planning cycle, and we're saying we need it in just a few years. And so it's really hard to get this industry to think about delivering the capacity that we think we need right away. And when I say it takes about 2 or 3 years to build a data center. Well, on the server side, it's even faster than that. I mean, these new generations turn in like a year and a half and stuff like that. So you got something that turns in maybe a year and a half, and you got another industry that plans on like 15, 20-year planning horizons. Is on-site I mean, it's gonna have to work temporarily, but man, I don't know actually. A lot of data centers are saying, listen, I can put in some power plants until the grid catches up, right? And so we call that bridging. So that seems to be the most pragmatic approach, but yeah, we'll see. Did you design that Elon Musk data center?
No, but Elon gets plenty of press just in his own right? So, yeah, we're seeing a lot of demand for what we call behind-the-meter power solutions, but as Sean said, it's really more of a bridging solution. And the reason being, we can't get the economics to work. So behind all these big mega projects, you got investors, and they have to get a return on their money. Well, what do you do if you put a power plant behind the meter, and it's got to just provide power only to that data center? Well, is that data center going to have a full ramp of the power day one? No. Nobody puts in 10,000 servers just day one. There's usually a ramp up period there. Well, what are you doing while it's waiting to get ramped up? What if it never goes all the way up? So you're selling some of the power back to the utility? Well, not every utility permits that throughout the US. There's only a few of the deregulated markets out there that'll allow you to do that. And at what rate are you selling it back? So there's a lot of challenges with having to do this behind the meter thing. Really what everybody wants to do is build a power plant like next to the data center, connect it to the grid, get a nice return on it like they would with anybody else building the power plant, and the data center just happens to also be one of those loads on the grid. It's also very hard to get the same level of availability. If you think about it, no one power plant has like 5 nines availability. They won't guarantee that. But if you go out on the grid as a whole, they will, more or less. And we back that up by putting generators on site so we get there. But if you build a power plant, all it's serving is that data center, it's hard to get similar availability of that power plant as it is coming from the grid. And so this is the tug of war that we're in the middle of right now as an industry and as consumers off the power off the grid. And yes, adding more capacity is raising some of the rates. You've already heard some of the utilities like freezing their rates, and you're finding them get new creative solutions to stop that. It's all TBD.
There's one more issue, and this is really interesting. And maybe you've dealt with, if you have, I'd like to hear some stories about it. But putting a power plant dedicated to a data center might not work. There's been a lot of cases where the data center can actually break power plants, can snap the shafts inside the power plants due to something called subsynchronous oscillation. So his servers are sitting there and they're doing these workloads that are jumping up and down, but when you aggregate that up to millions of servers, all of that load hitting these power plants, seconds going up and down, they're not designed for that. Is that something that you're dealing with?
You got to buffer it with a lot of battery. So you got to put a big dampener, electrical dampener in the mix in order to deal with it. There's really no other way. And so that's another reason why nobody wants to just directly couple a 380 megawatt combustion turbine onto a data center, especially an AI load data center, because those loads can oscillate and have all sorts of different swings that can cause havoc on a power plant.
And then my other question is, are you doing things to make servers more generator friendly?
So I think we have to. I think a lot of this comes back to the software, though, right? Is what are the dynamics of the software, how they want to utilize the hardware resources, right? So, particularly in the AI world today, that's a big issue, right? You have these workloads that somebody kicks off, they're trying to train one of these large language models, they kick off this load and, you get 10, 15, 20 megawatts of power, almost instantaneously. That thing finishes and you drop 20 megawatts of power, right? So I think there's a whole area of opportunity out there around this like hardware, software, co-optimization, right? I think, it's not just what's going on at the hardware, it's the entire ecosystem, the picture, right? How are we designing software that plays into these mechanical systems that we have, right? I mean, I've heard Dave use the term mechanical systems don't move at the speed of light and software moves at the speed of light, right? So by its nature, you have this discontinuity in what you can actually do from being able to react with a mechanical system versus an electrical system or optical system that moves at much different speed than we can in the mechanical world, right? So it's I'd say end to end, no matter what kind of discipline you are, whether you're a software engineer, a computer engineer, a mechanical engineer, a water engineer, all of these disciplines have to work together if we're going to make this whole system work, because any one of those doesn't kind of play their part, the whole thing collapses pretty much, right? So
I'm glad you introduced that topic. That's what I was going to ask next. So let's talk about engineering. We have engineering students here, and some of you are electrical engineers, some of you are mechanical engineers, chemical engineers, et cetera. Can we talk a little bit about two things that basically need to be re-engineered? One of them is power, right? How are we going to deal with these enormous amounts of power going into, let's say, equipment racks? The second one is cooling. How are we going to cool these really, really dense structures? So you're a cooling engineer. Kick us off on that.
yeah, so from I'm a mechanical engineer. So we're moving to this paradigm of liquid cooling, right? So instead of using air, we're now putting these things that we call cold plates on top of these chips. These cold plates have channels in them that are on the order of 50 microns, right? So literally a piece of hair gets stuck in this, it can destroy the entire system. It can block the channels, it can stop the cooling. So I think and I'll get to where I need help, right? So there's a lot of challenges from a mechanical engineering perspective. How do you design these things? How do you manufacture them with reliability, right? The area where I think the industry needs the most help is actually chemists and chemical engineers and material scientists. We've been doing these big water cooling loops for a long time, where you have these big plate heat exchangers, for example, with fin gaps that are large, right? So you could get all kinds of crud and junk in your water system, and probably not going to impact it, right? I mean, you know, if you, like I said, if you get a hair in one of these cold plate systems, you know, it's disaster. And so an area that I see necessary is how do we get better collaboration between mechanical engineers and material scientists, material engineers. What are the right materials that we can prevent corrosion in these systems? How do we do treatment of these chemicals? Because some of these systems that we're designing today, they have to be deployed and they have to be out there for 10 years when you can't touch them. There's no touching them. There's not like your car where you can come in and do maintenance and, you know, change the, you know, drain the fluid out and put new fluid in, right? You know, these are mission critical things. They have to be up and operational 24/7, 365. So how do you do all these things? So just one example where, like, me as a mechanical engineer, I can't do my job unless I have material scientists, chemists, chemical engineers, right? All these other disciplines that you probably say, what are they, you know, do they have roles in the data center? Yes.
How many mechanical engineers in the room? Show of hands.
Wow.
How about electrical?
Okay.
Other? All right. So like almost the third. Really good. Okay, need all of you. Like, you're hired.
You're hired.
So like the demand is unprecedented right now. What you're going to see over the next 5 to 10 years is the data center industry is going to draw down the largest amount of resource of any industry ever. Like, quote me on it. It's going to draw down literally everything in order to make what we're trying to build happen. And on the surface, you could say, geez, we're going to build all these huge data centers, we're going to add all these more power plants, isn't this really bad for the environment? Yeah, it is if we don't do it the right way. If we don't, like, collectively figure out a more sustainable way to make that happen, yeah, it's going to be a bad thing. But on the flip side, the software, the AI solutions that's coming out of it are helping solve problems that we would have never been able to solve otherwise. And so I would argue, yeah, we're probably going to have some short-term pain here to have the long-term gain. And that's kind of the bigger picture with this. The solutions that are going to come out of it are going to solve for these big worldly problems. But we're going to need an enormous amount of brain power in a very short amount of time here to basically re-engineer everything that we've done in this space, like top to bottom. It all needs redone. And I'm not talking about just once. Just in the span of the 2 years, like literally every conference we go to, it's like, oh my gosh, it's changing again. What, we're going up to a megawatt a rack? What, somebody's talking about 2 megawatt a rack? Yeah. 2 megawatts a rack is like a Caterpillar generator, the big ones that you see on the semi-trucks in the back in a giant container. A 1 megawatt is like a semi-truck that's pulling all the freight, 18,000 pounds on the highway. So that's it. We're saying that's in one rack. One data center rack. That's like the footprint of this that I'm sitting in, inside of a data center. It's insane amount of power in one spot, and now multiply that times tens of thousands, tens and tens of thousands. How do we deal with that, right? That's the scale of the problem.
So the acceptance of liquid cooling, in my view, is like a big milestone, right? I smile with Sean because when I first met you, we didn't think liquid cooling would ever be a thing, right? At least you told me so, Sean.
Yeah, I think I lost that bet.
Lost that bet.
Yeah, I think
Where's the 20 bucks,
I think I owe you the 20, yeah.
Give it back.
But what's your perspective now? And I mean, what's the future of liquid cooling? Because it's clear that the era of cooling these gigantic electronic machines with liquid is now here, and it's here to stay. So can we talk a little bit about that future? For example, you talked about, Dustin, about direct-to-chip with cold plates. But there's another method of doing it, which is take the server and put it directly into the liquid. It's called immersion cooling. Can we talk a little bit about what you all see as the future?
So here's why we went away from cooling computers with liquid. You know, one time you had these mainframe type computers. So I'm talking like 70s, 80s, and it was a whole bunch of compute in a very, very small space. Sound familiar? And these were doing hardcore calculations, generating a lot of heat, and so we were circulating cooling water through those to keep those things stable But why did we move away from something like that? And now why did we move away from liquid cooling? Why are we moving back to it? Well, first, from my perspective as a data center developer, air is cheap. And so when we were going to the type of compute that didn't, we're just moving pictures around and, websites and stuff like that, well, you don't need that hardcore computation. I could spread the computers out across a building and then just blow cool air on them. And then there was this big push to make data centers much more energy efficient. And we just started using outside air to cool all the servers. Life was good. We don't have chillers, we have less equipment, it costs less. It's super simple to operate. I mean, it worked out really, really well. Well, now we're going back into this hardcore computational, hardcore computing environment, and now we're having to bring all this back. Liquid cooling look, air is an insulator. If you open up your wall, you've got insulation in there that's used to trap air because air is such a good insulator. Water is and liquid generally is just a great means to move heat. Here's an example. If you're ever cold one day and winter's coming, you could stand in front of the heater and blow warm air on you, stuff like that. Or, try this, go wash your hands in warm to hot water. And that heat transfer on all the veins, that conductive heat transfer will warm your body much, much faster. Or jump in the shower or something like that. And so that's where we're having to transition things. Now, you could continue to cool these racks that he's talking about that are using a lot more heat. You could do that with air, but you need to move more and more air. And we're modeling this, and at a certain point, as the heat density goes up, like you're moving like a Hurricane Katrina through these things, right? It's just not practical versus some hoses and some tubes that are much, much smaller. And that's where we're going. So now the innovation is, what's the most optimal way to do that? And if you go check out some of the labs that are here in Villanova, that's what's being optimized and tweaked, is what's the best way to extract the heat off of the chip onto that liquid medium.
How about power? How about this enormous amount of power that has to go into a rack? Isn't that a problem? Isn't that a lot of current, for example? And doesn't that cause heating?
I mean, when I think about the amount of power that we're talking about, say, going into a rack, it's a lot. Is that an engineering problem?
It's a huge engineering problem because you have to get the power to it. That's an engineering problem. But then you got to get the power to it safely. We're talking about an enormous amount of current in a very small space where people are walking around. And so this is where, I look to my data center engineering core and be like, look, okay, not only do we have to do this, but we have to do it safe.
Yeah, so back to the 15 amp breaker that Sean mentioned previously, that's typically on a 120 or 220 volt circuit. In a data center, we're commonly using like 415, 460, 480 volt circuits to put the power out to the floor. That worked when we were 10 kilowatt a rack. It works when we're 50. It works when we're 100. It works arguably up to about 500. And now beyond that, it starts to look stupid. Like the amount of copper that we have to run from point A to point B and the amount of copper we have to run down inside that rack is a lot. So now we're having to re-engineer even the power in the data center. We're having to look at higher voltages and using Ohm's law to our advantage. So going up to 800 volts DC or 1500 volts DC, and notice I said DC, not AC, so direct current, trying to get rid of all of the transformer losses and the conversion losses that occur when we have to switch from AC to DC. So power coming off the grid is coming in at AC, power going into the rack is DC, right? All of the computers operate on direct current. So somewhere in there we have to do a conversion, and in a lot of data centers we end up doing a double conversion in there because we have to have this battery storage piece in the middle. And so really inefficient. Ideally, what we would do, come off the grid into a substation, go right onto a high voltage DC bus, tie some batteries into it, tie our other sources into that, and connect up our servers. I'm greatly oversimplifying it here, but that's ideally what we would do. It would be the most energy efficient. We have the least amount of losses and the least amount of copper, which all has to be supported structurally and everything else, and via cooling systems. So that problem has to be solved. Right now, we aren't doing 800 volt DC direct in or 1500 volt DC direct in, certainly not on any scale. So again, lots of engineering challenges ahead on both the mechanical and electrical and the chemical.
And I think, at the end of the day, right, we're powering these semiconductor devices. They run at 1 volt DC. So we got to take power at whatever 13,000 volt or whatever it's coming in and bring it down to 1 volt. So, it's all those challenges. It's getting the power there, but then, once it's there, you're also doing all kinds of power conversion inside of these systems to get it to the voltage that's needed to make all these devices work and work reliably, right? I mean, that's a big deal. Heat is the enemy of reliability, right? So you look at these semiconductor devices, thermal management is critical from a reliability perspective. And so it's why all these things we're doing from a power perspective, from a cooling perspective, are so critical, because at the end of the day, it's about reliability of all these devices too. So
It's worth mentioning, I don't know if this is common knowledge or not, but I'm gonna throw it out anyway. So the lights here are only on because there's turbines turning someplace in a power plant, right? Or there's some photovoltaic cells picking that up. And they're pushing out power at like 12,000 volts, and then it's getting stepped up to like 135 or 345,000 volts out on those transmission lines. Then it's getting stepped down to some lower voltage on the distribution poles that you drive by every day on the roads. Then we have to step it down again through some transformers and distribution gear in the data center, and then we get inside the data hall. We have to transform, rectify, step it down again, get it to the rack, to a power supply there that then is stepping it down again and again and again. So we're like typically coming in the rack at, on the other side of the power supply at what?
220.
Yeah, we're coming in at 220, and on the other side we're,
1 by the time it gets.
by the time we do multiple steps down.
Yeah.
So like,
12 volt.
You're at 12 volt at the outside.
yeah,
of
we
your
have
house.
12 volt, yeah, exactly, DC. So that's a lot of changes in the power to get it from point A to point B. And that's really inefficient. And now that we have such a massive amount consolidated in a tiny footprint there, 1 megawatt rack, it's a much bigger problem to solve.
That's concerning. Right? Well, it's concerning because it's a question of efficiency, which kind of leads to our last sort of topic. And then we'll throw it open for questions. The topic of sustainability, right? The topic of how do we make data centers resilient and sustainable, right? And I know, Dustin, you've done quite a bit of work on this recently. So I wonder, can you give us your perspective on the sustainability aspect of data centers?
Sure. Yeah, so clearly an incredibly important topic, right? I mean, in order to do all the things we want to do, if we're not doing them responsibly, to me, I don't know that it makes a lot of sense, right? And so, there's a few things in the data center world. I mean, the data center has 2 big problems from a sustainability. One is the power side, which I think we talked a lot about, right? I mean, if we're going to power all these things, we have to figure out how to do this with carbon-free energy, right? The other side of it is, the data center has a lot of stuff, right? So if anybody's familiar with sort of how we look at the greenhouse gases associated with systems, we kind of talk about scope 1, 2, and 3 emissions. So scope 1, not that relevant in the data center. So scope 2 is the electricity. So we have to solve that. And then, scope 3 is all the stuff, right? What's the environmental cost of actually building all of this, right? And this is where I think we have to look broader than just the data center industry, right? This is an ecosystem thing, right? At the end of the day, this includes how are we manufacturing these semiconductor devices? How are we building all this cooling equipment? How are we thinking about, well, we have these GPUs today that, literally people are, next one comes out next year, they're throwing out the other ones and taking the new ones because they're, give a much better price performance than the old ones, right? But we have to think about this as a holistic kind of ecosystem, right? And look at not just that energy piece, but the overall kind of scope 3 piece too. And I think there is a huge opportunity there, right, for us to think about how do we do this better? How do we manufacture things more responsibly? How do we think about reuse and recycling and all these things that come along with kind of the scope 3 as another important aspect of sustainability that I'd say in the last year or two has been getting, some look and mention there. I know there's an Open Compute project, which is a industry open source community that many of us participate in. There is a lot of work on how do we start to look at the life cycle assessment of all of these systems, right? Because we have to kind of think about this holistically, not just as any one piece of this puzzle. So.
What about water? Do
Water?
data centers use water? Anybody? They use water? Yeah? Okay. Do they waste water? Yeah? Okay.
Probably.
It depends. So they only waste it if they're using an adiabatic form of heat rejection. So they're basically evaporating it out into the atmosphere and disrupting basically our water cycle, aquifers, reservoirs, et cetera. And so they all use it nowadays. Al said it, hey, we're really dense now. So we have to use it in order to cool the chips, but we can put it in a closed loop cycle. So it's just sitting there recirculating, and we're not actually wasting it. There's nothing going down the drain. There's nothing being evaporated out to the atmosphere. The bulk of today's data centers are built so that they use water, but they don't waste it. They aren't using an adiabatic form. There are data centers out there that have cooling towers that are open, that are adiabatic, and they are expelling that water into the atmosphere. A lot of them are in places where that's fine. There's a high availability of water to do so. Some are not. But by and large, I think that's one big misconception in the industry right now is that they're not wasting it anymore. They're still using it. Most data centers are built so that they're not wasting it. But that said, that's not really energy efficient. We use more carbon on site with a closed loop system with like air-cooled chillers than if we were using an adiabatic form. So we haven't really fixed the whole problem. We fixed part of the problem, and we kicked the other part down the road. So, something I had proposed in another conference is a water usage credit or a WALC. So like a renewable energy credit, why don't we start contributing and funding a renewable water source, build dams, reservoirs, et cetera, so that we can then use it on site where it's more energy efficient. Food for thought. But we got to start thinking more holistically on the sustainability problem, back to Dustin's point on Scope 2 emissions.
Are there any sustainable engineering students here? We have a sustainable engineering program, there's at least one.
All right, so my message landed with 2 people. 3.
Well, I was going to say, I heard the dean
nice.
say every engineer has to be a sustainable
Hey,
engineer.
Mark, that was I didn't plant that, but I might have planted that.
You did plant it, and with that thought, we're going to open the floor for questions, and then we'll finish up and ask you all with some closing comments. Questions from the floor, please. I'm sure there are some. There's a mic up here.
Microphone right over here,
please,
if anyone has questions.
Thank you. That was most interesting, right? I didn't realize the different dimensions of the problem. I knew the power side of it. I didn't know the other parts of it. But this is just a point of clarification. And you mentioned that some of these racks that you have 1 megawatt of heat emission, right? So how many servers do you put in a rack? I mean, what's the number you're talking about in one single rack? Thanks.
It's an abstract question, and this is why I've got a data center that I just turned on in Milwaukee. It's like 1 million square feet. It's one server in 1 million square feet. Because what I've done is I've got in every single GPU, I've networked all those things together so that they all act as one computer.
Okay.
So I know what you're asking, but that's the real answer is what we're trying to do at the end of the day with these AI training data centers is create a giant supercomputer.
I'll answer it a different way and perhaps more direct. So we used to design racks to take like 42U or units of server racks, right? But as we change the form factor of the server, going beyond air-cooled to liquid-cooled, the U per server has really become this abstract thing. It's not really measured the way it was before. What's still measured the way it was before is the rack, dimensionally. So we're still solving for this three-dimensional problem where it's how many of these servers, or chips as it were, CPUs and GPUs, can we get per unit area in a building. And the economics of that are really what drives us to still stick with a vertical form factor in most data center applications today. And it's why you don't see most converting to immersion, where the servers are dipped in a tank and it's put on its side. It's because we changed the yield. You change the economics of the problem. How many servers can I fit in a data center when I've got them turned on side versus upright? You also change the economics of the operations and maintenance. And so at the end of the day, all these are financed. There's people backing these with loans and all sorts of financial instruments to pay for them, and they want a return on that money. And at some point, it just doesn't work for different software applications. So we still are putting them, we're still racking these things in the servers vertically like we were before when they were air-cooled. And in fact, this is something we probably should have covered earlier. Does everybody know that all the liquid-cooled servers are also air-cooled? Right? We still have an air-cooled element to them. Okay, about 20%, just round numbers, 20% is air-cooled on a liquid-cooled server. 80% of the load of it is liquid. It's going out via water, 25 polypropylene glycol, or refrigerant. And so we've got both in the mix now that we have to solve for.
Thank you.
Hello, I was wondering, with Microsoft having a new state of matter apparently discovered, if that'll affect data centers at all, and if so, when it'll start doing so.
Would you mind saying that again? I couldn't hear.
Sorry, can you hear me when I'm speaking like this?
That's better, yeah.
Great. With Microsoft having discovered a new state of matter apparently months ago, I was wondering if that'll affect data centers at all, and if so, when it'll do so.
Yeah, okay, so you're asking about quantum computing. And quantum computing is the next thing. So right now we've got AI with these accelerators like GPUs and TPUs and stuff like that. But the next sort of level that we're all trying to engineer is taking quantum and doing it with, and doing this type of computation with the quantum computer, so it's much, much faster. The extra state, the new state of matter is only one way. There's many different ways that people are trying to exploit the quantum effects in order to do computation. So we'll see which one actually wins.
Thank you.
I think the key to that, though, is
Go ahead.
just like GPUs, right? So what you didn't see happen was these GPUs came out and everybody said, all right, let's throw away these CPUs. We don't need them anymore, right? This is a additive industry, right? Yeah. Every time we come out with one of these things, whether it's a GPU or whether it's quantum, it just is a new way of doing something more efficiently, but it doesn't solve every problem. So we're going to be in this data center world where people are going to come out with, whether it's quantum or the next technology that are all going to be additive.
They're complementary to one another. They are not replacements for each other. In fact, you'll probably see future computers where you've got all of them in the fold doing the computations. They're just doing different computations.
Thank you all.
Hey there. My question is for Sean. I heard recently about Microsoft working to reopen one of the units at 3 Mile Island, and I wanted to know if this is part of a larger plan for Microsoft to get this data center energy from a clean source, or if it was just a convenient way to get such a huge amount of energy.
Yeah, thanks for bringing that up. Every time, of course we're in Pennsylvania, I think you guys understand this, but every time this comes up, I always tell people, no, not that 3 Mile Island, the other one. The one that was running perfectly fine up until a few years ago when the company who owned it shut it down, because it just wasn't making money. The economics have changed, right? And so now the data center industry needs as much power as possible. Ideally, we want carbon-free power that is baseload, that is firm, that is running all the time. Sure, we could build a bunch of wind turbines and PV things, but everyone demands their internet to be available all the time and not just when the sun's shining, right? So that's the issue there. So yeah, nuclear offers baseload power that's carbon-free, and extending the life of nuclear plants is one of the most cheapest forms of energy. Forget, carbon-free or sustainable or anything like that. Just taking a power plant and just going in there and updating all the safety systems and rebuilding things and just extending the life. There's not a lot of those opportunities. 3 Mile Island was one of those opportunities.
That's great. Thank you so much.
Hi, excellent talk. Nice to have this distinguished panel here. So I'm a first-year PhD student in mechanical engineering, and I'm focusing on AI and sustainability. So my question is, in the beginning of the talk, our dean, I don't remember her name, she mentioned in next 10 years, we are expecting like 10% of US power consumption is going to be, the data centers will be equal to that. And you mentioned about ENIAC, 1960s, and then supercomputers, and they have the computation power in our phone, laptops, now data centers. Where do you see this going in the next 5 years, 10 years, 15 years?
I wish somebody knew. I mean, clearly AI is evolving, right? Just look at what's happened since kind of ChatGPT, what was it, 2.5 years ago now, right? AI became a thing that computer scientists did in the lab, and and now it is something that I literally use it every day to like plan my day and figure out something I don't know. And now we're evolving into agentic AI, where you're going to have AI systems that are going to be able to automatically understand other systems that they can communicate with. So we're evolving from having one of these large language models like ChatGPT or whatever, pick your favorite large language model, to now all of these large language models, some that are tuned for certain applications. And so we're going from one thing to now having lots of things that have to all communicate with each other. So I don't think that AI is gonna go away. I think more and more we're gonna learn and understand how can we leverage AI, and I do think there's a lot that can be done from a doing it sustainably and responsibly perspective. Like, how do you build the models that are what the industry has been calling kind of like small language models, or like domain specific models, right? So I don't know. I think
many more data centers.
Yeah.
That's the answer. We've never stopped the pursuit of increased intelligence and knowledge. Right? So now we've invented a tool where we're able to put that on steroids. So the challenge now for us is not only to use that tool, to solve the everyday little things, but to solve these much bigger problems, which the tool itself is creating now. This is the irony, right? So we need to leverage the tool to solve the problem that the tool is creating, as well as solve all these other big worldly problems. I think just significantly more data centers is what you're going to see as a byproduct of that.
Okay. Then it questions the cooling. Again, you have to have water cool, air cooling, or placing it close to water resource like over a lake, or what do you call, maybe Alaska?
You'll see both liquid and air.
And air.
Again, every liquid to chip application still has air for the different peripheral and parts on a motherboard that's not a chip. And so you'll have combinations of both in the mix for the foreseeable future. Let's just say the minimum of the next 5 years. And in terms of placement of data centers, the cost of fiber has come down so much, per mile, to where we're putting data centers out in really remote locations now. But we still have that problem I mentioned before. The speed of light is too slow. So we still have to spread these things around, and we don't get the liberty to just put them wherever we want. They are geographic dependent based on the application and the people and the things that are using that software. So you still have to keep those points of presence close to their users, and that's going to cause a proliferation of data centers. Again, it's all software dependent.
Makes sense. Thank you.
How about one more question, please?
I'm just asking about, so you talked about earlier about how with microgrids where there's a challenge with directly coupling these generators with like an AI workload where the AI workload's constantly changing, turning on and turning off. How does this affect currently grids, like primary grids that are kind of supplying power to these, especially with these AI workloads or other kind of data center disconnects that are going on, especially in these super localized areas like Data Center Valley?
Not good.
Well, there's two issues. There's the issue that I talked about where the servers jump up and down. So that's an engineering problem to go after. That's a great one. The other one is the size of the data centers. So Dave was talking about 1 gigawatt, 2 gigawatt, 8 gigawatt data centers. That much load centralized on the grid creates an extremely huge vulnerability. If those data centers go down, all of that load coming off the grid at that one particular point in time would cause havoc on a grid. And so this is something that we're working with the utilities on, like, how are we gonna solve this? Because if there's any sort of power and not like a brownout, you know, be sitting in your house and the lights dim a little bit, no big deal. But the way Dave designs my data centers is that if the power quality gets bad enough, we'll just trip offline and go on to on-site generators. So you can imagine if there was all of these data centers around, you know, 10 gigawatts, 20 gigawatts, that some brownout happens and the grid loses all that load, it's enormously disruptive. And so that's another really fun engineering problem that we're going after, that we're trying to solve right now.
Batteries is the main answer. They're just deploying more large-scale battery energy solutions, or what they call BESS, to act as that shock absorber to deal with those situations. So, but again, the issue is we're not building the batteries fast enough. I know that sounds crazy, but it's true, because we have the demand simultaneously with the servers and the cars, and so we just have all these things pulling on that particular resource right now. But battery will be the primary answer. There's many others, though.
Then following up on that battery idea, kind of how do you also protect these batteries that aren't kind of necessarily designed for the quick kind of discharge or kind of recharge for these kind of instantaneous workload shifts?
That's a good question. Yeah. Why don't you take it, Dave?
Yeah, sure. I mean, lithium-ion batteries are pretty good at handling the big load swings, and once you get over a certain scale, you know, it's like a supercapacitor. It depends on the type of battery, and it depends on the size load and the frequency of the loads that we're talking about. But short version is lithium-ion is able to handle the grid scale shock absorber type of load swings. I think the manufacturers at the sub-cycle level have already figured out answers for that, be it the UPS manufacturers or generators. They've already made modifications to their software algorithms or the governor on the generators to be able to accommodate those really high frequency loads. But add to it, I'm sure you got more.
Yeah, as long as they're available. I mean,
Yes.
all of this equipment is very scarce right now. Yeah. Very scarce.
Thank you very much.
Thank you.
So I think we're on time, but I would like to give you guys one last opportunity to convey some message that, you know, is top of your mind to our students. We really appreciate all the students that came here today, and I hope it was worth your time. Also, staff and faculty were here. What's one last thought you might want to leave this audience before we close? We'll start with you, Dustin, and then Sean and Dave.
Yeah, sure. So I think one of the challenges I've seen, and we talked a little bit about this earlier, is the need for more and more, you know, collaboration and cooperation, right? So one of the challenges we see in this industry is, you know, I came out of school as a mechanical engineer, and sure, I knew most of what I was supposed to about mechanical engineering. I could derive the Navier-Stokes equations, whatever. I didn't know anything about electrical engineering. I barely even knew the kids in the other class, right? So, you know, a piece of advice is we need to figure out how we better collaborate. Like, go and meet your electrical engineering colleagues and your chemical engineering colleagues. Like, do a project with them, because where we struggle is we get great students coming out, and then it takes a year just to get them to be able to kind of talk the language of their colleagues that are structural engineers or chemical engineers, et cetera. And so that would be my advice is, clearly you have your work to do to get your degree and do your work you need to do, but meet some other people, do some projects, things like that. So
I've got 2 pieces of advice. Number 1, use sunscreen. Number 2 is don't be afraid to be multidisciplined or multi-domained. These problems require thinking about many different engineering challenges and how they react in the system and how they all change each other. So don't be like, because I've heard people say, well, I'm a mechanical engineer. You're going to have to talk to that person over there. That is the old way of thinking. The new way of thinking in my industry is you're thinking about all these different domains at once.
My advice, we're in the 5th industrial revolution. I believe that we're going through the largest single change ever in mankind's history right now. You're living in it. And you happen to be living in it at a time when you're coming out with a lot of knowledge from a great university. Put it to work in this industry. We are not going to have enough people to do what needs to be done, and the amount of problems, the scale of the problems that need solved now are unlike anything we've ever had to deal with before. So, huge opportunity in front of you in the data center industry, and there's just a wide range of opportunity within that space. So, good luck.
So with that, would you all help me to thank our guests today for their wonderful presence? Thank you all.
Thank you, Dustin.